The next talk is going to be given by Britta New, and when Britta came to the Institute, the Hamilton Carr Institute, after doing her master's degree at Northumbria, when she started talking about the fact that she was repairing and reconstructing her own house, I realized that perhaps she might be somebody who would be interested in doing some panel work, and that has proved to be the case. And so the project that she's going to talk about was worked on with Ray Marchant, who came to the Institute from the early 1990s as a teacher to teach structural panel conservation, largely by working with an individual student on a particular project. And this is the results, the talk that Britta will give is the results of a particular collaboration. And just to say briefly a little bit about Ray, he had a background in engineering design. He's the co-author of the paper, and then moved into sort of carpentry and working on a wide range of projects. You need to get him to sort of over dinner to tell him something of his past career. And he then worked with Simon Bobak at Ebury Street from 1985 to the present. And as all of you know, he's contributed to various conferences and given a number of papers, and including the account of the conservation of the large Sanderdam painting from Upton House, part of the National Trust, which actually came here some years ago as part of the Sanderdam exhibition. And the work that was done on the panel painting made it, in fact, perfectly safe to travel to the exhibition and return, and also go to Holland. Britta, so if you'd like to come to the podium, and we'll set up her talk.
Thank you, Ian. This paper has been prepared to illustrate and hopefully to explain some of the repair and support techniques used at Ebury Street Studios in London and at the Hamilton Carr Institute in Cambridge. It's primarily a case study describing the treatment of a 16th century Flemish triptych from the Fitzwilliam Museum in Cambridge. The painting first came to my attention when Ian McClure, who was then the director of the Hamilton Carr Institute, asked me to prepare a condition report prior to its inclusion in a Times article relating to the ongoing deterioration of a number of national artworks. And you can see the dramatic raking light image of the photograph, of the painting up there, which sparked a generous donation, allowing the conservation work to be carried out. And here you can just see the raking light image displayed a little more clearly. This is just the central panel of the triptych. The triptych's composed of a central panel depicting the Deposition and two wings depicting the Presentation and the Marriage of the Virgin. The difference in style and quality between the wings and the central panel is quite clear here, even in the before-treatment photographs. Dendrochronology also supports this discrepancy, dating the Deposition at approximately a quarter of a century earlier than the wings, with an earliest felling date of 1465. I'm going to talk briefly about the condition and the treatment of the wings, and then go on to the more complex issues in the Deposition. The wings both measure 102 centimetres by 39 centimetres. Both are made up from a high-quality Eastern Baltic oak, and they've got a vertical grain with a slightly tangential cut. They were constructed from two boards with a simple dowelled butt join that you can see illustrated here. And they've been quite clearly sawn in half. You can see the marks on the backs of the panels, and in the detail you can also see the exposed dowels. They now measure 2 to 2.5 millimetres in thickness, and so presumably they would have begun life as double-sided wings measuring 6 to 7 millimetres in thickness. They're stuck to crude pine cradles which were jammed, and they developed a vertical concave warp and slight horizontal washboarding top and bottom. The horizontal members of the cradle here you can see extending beyond the ends of the cradle, indicating that their cross-grain shrinkage has been ongoing since the cradle was applied. You can also see how the adhesive was beginning to fail. Between the panel and the cradle in the panel of the marriage. You can also see the sort of fracture that's beginning to develop in the structure of the wood caused by the restraint of the fixed cradle members. And you can see the fixed cradle member just at the bottom there. The wings were both cleaned and given an isolating coat of paralloid B72. We chose B72 because of its stability and also the fact that it needs a higher aromatic solvent than other possible varnishes, such as Regal Res or Archon P90 or Ketone N, making it more effective at isolating against facing adhesives such as Beaver 371 or paralloid B67. Theoretically, its high molecular weight and consequently poor spectral qualities as a varnish may well give a better tooth for a facing to stick to as well. Before we commenced the structural work, profiles of the edges of the panels were traced. We wanted to assess the stability of the panels when the jammed cradles were released before we actually began work. The exposed parts of the sliding members of the cradle were planed down, and as you can see here, sash clamps were used to ease them along, allowing the newly exposed regions to then be planed down until the members could be fully removed, and they were then lightly planed on all sides and replaced. We also then made cuts in the fixed cradle members to allow some lateral freedom of movement, and we could then observe the panels over some weeks with varying levels of relative humidity. The marriage showed less deflection with changes in RH, indicating that it had a greater stability. And as this cradle was also partially delaminating, it made it a good candidate to begin work on. We were working at an elevated RH, and the painting was faced with a 5% sturgeon glue brushed through a lightweight wet strength paper. We chose this aqueous adhesive because of the good surface conformation it provided over the paint surface, but also its compatibility with the fracture repair adhesives that we'd be using. We didn't want to introduce something synthetic to the front that might compromise an already minimal gluing surface. The cradle was then chiselled down to a veneer, as you can see here, working from the outside into the centre of the panel. And the veneers were then further thinned using a plane until they were of a thickness that allowed the glue to be swollen with laponite and removed. And you can just see that in the foreground here, where those veneers are being swollen. After the cradle was removed, the panel was again observed over time under varying humidities. It appeared quite stable, and the curvature didn't alter significantly, so the other wing was treated in the same way. During this treatment, however, of the presentation, it was noticed that the facing had caused an increase in the convex curvature from the moisture penetrating the structure, and this led to some developments in the facing for the central panel, and I'll go on to explain them shortly. Once the cradles had both been removed and the small number of fractures repaired, new supports were made to allow for safe handling and framing. And this type of support, you probably already know, is described in detail in Ray Marchant's paper in the 1995 Getty proceedings. But in brief, I'll just explain. They consist of a series of diamond-shaped Sitka spruce battens which are held in contact with the panel across the grain, and the tapering ends allow for some deflection of the panel at the edges. These are just held against the panel by a series of vertical gelutong strips, and those are attached to the panel, just glued to the panel, by small C-shaped oak retaining blocks. And these discrete points of attachment are the only part of the structure that are actually attached to the panel, and they're far more accommodating to movement than those of some sort of traditional cradle structure. The spruce battens, the tapering battens, again, were then held in relative position to each other by means of a pair of gelutong strips. We also then added gelutong and foam backstrings to each tapered batten, and these are visible, just these horizontal areas here. The panels were framed using a rigid central beam, which was recessed into a build-up on the reverse of the frame, and it applies pressure on the tapering battens via those back springs that I've just shown you, holding the panel within the frame across its entire width rather than just at the top and the bottom edges. It also allows some freedom of movement due to the flexibility of the spring system. And here are the two wings, repaired, restored and framed. And the work on the wings proved to be quite a valuable exercise in forming the subsequent treatment of the central panel. So I'll move on to the deposition. It measures 101 centimetres by 72 centimetres. It's made up from 4 boards of Eastern Baltic oak cut from 3 different trees. It's got a vertical grain and a slightly tangential cut like the wings. But this has been radically thinned. It now only measures between 1 and 2 millimetres in depth. And because of this, any further details of the construction of the joints has been lost. You can also see here the very heavy mahogany cradle with blind ends that was applied to the reverse of the panel, presumably in the 19th century, with several subsequent what you might call improvements. To begin with, one of the fixed central members had been enlarged to reinforce a split that had developed the full length of the panel beside the original cradle member. Then several oak blocks had been glued between the cradle members, again as reinforcement for damage, also probably caused by the cradle, but these just would have served to have locked the cradle movement further. And finally, just to add insult to injury, a series of beech blocks were adhered, mainly to the ends of the panel, with the grain running perpendicular to the panel. And it was the response of these blocks to changes in RH that have probably caused the worst of the panel's deformations. I'll just bring you back to the raking light photograph. It illustrates the terrible condition that the panel was in before the treatment started. It's more akin to an unrolled manuscript than a panel painting. The yellow lines illustrate the board drawings, and the red lines, the splits in the wood. There were about 64 in total, I think. The shaded regions indicate the worst of the deformations. And when you then superimpose the cradle onto the raking light image, it's quite clear that the damage is directly related to the application of the cradle. And here you can just see it again without those markings. Some of the other problems or deformations worth noting are the pinholes that have been made by the panel being nailed from the front onto a cradle member. You can also see the loss of a few millimetres of the support at the joint between the third and the fourth boards, particularly in the misalignment of the young man's brooch. You can see here the old repairs through Christ's body by the mismatched retouchings, but you can also see the new fractures that have been caused by the shrinkage of the panel under such a heavy restraint. And there was also tension on the varnish surface, which was beginning to fracture and break away. During cleaning, it became quite clear that the other board joints had also lost some material. The central joint was actually open across its entire length, and a great deal of filling had been obscuring how stepped the joint had been. The joint between the first and the second boards had a tapering bond meeting at the upper edge. It was partially held open by a fracture that developed just to the right of Christ's head, just here. And that was just one of the few regions where the first board was actually adhered to the second. Now, as I've already said, we had some concerns over the facing of the wings. In terms of the deposition, it was vital to provide a strong and even structural support for the paint surface while the work was carried out on the reverse. And it might even become necessary to build up or laminate the facing. The extent of damage to the panel indicated that it was still highly mobile, and we didn't know if there might be a tendency to curl as the panel, as the cradle was removed. And we were also concerned that some parts of the support might actually be missing. We wanted to use an aqueous facing to assure that there was good surface conformation and compatibility with the panel repair adhesives. But we were also concerned about the amount of moisture coming into contact with the panel. So we carried out some practical research into different papers and adhesives, and that led to the choice of a medium-weight handmade Japanese kozo paper. This has got long, strong fibres, good dimensional stability when drying, and a low wet strength, which allows it to shape itself to the panel surface. And the adhesive that we chose was a mixture of wheat starch paste, which supplies a bulk to help with the application, and some flexibility, and it also helps with the surface conformation. And to that, we made a small addition of sturgeon's glue to provide a slightly stronger adhesive power. The low wet strength of the kozo paper makes the transference of a join requiring a gap in the facing really simple. On this mock-up, a fracture is traced onto a sheet of Melanex. And the kozo can then be laid over the Melanex and the line traced with a wet paintbrush. The paper then tears very easily along the join, leaving a feathered edge, and the fibres of that edge can protect the vulnerable fragments along such a join. Or similarly, you can then butt them up to the next sheet without actually requiring an overlap, so there's a much more even exposure to moisture. We then wanted to reduce the amount of moisture when applying the facing, and that was done by an adapted method of application, based on a paper conservation method of working. The sheets of kozo were pre-stretched and cut to size, and they were then relaxed and held against a Melanex sheet by a light spray of water. And the adhesive was then applied to the paper very thinly and evenly and without any sort of attempt to saturate the paper. It was then lifted on the Melanex, turned over and positioned over the surface, and then the Melanex was brushed down to ensure that there was a good surface contact. We could then peel the Melanex away and dry brush and tamp down the surface. And to further reduce the effects of moisture, you can use blotting paper to draw moisture from the surface. When it's dry, the facing has got a high shear strength and a low peel strength, which allows it to be removed dry. And the feathered edges are also initially really difficult to lift, which makes accidental peeling when you're working very, very unlikely. So this is what we chose. The deposition was faced with 2 layers of this combination, leaving a gap between the 2 panel joins that were likely to come apart easily. And here you can just see how good the surface conformation of the facing is. We'd made a contingency plan as well to heat seal a beaver impregnated canvas to the facing, which we could then loom if necessary to hold the painting flat. And so moving on to the structural work. As the cradle members were jammed, it was necessary to open up the blind ends to see if they could be freed. We used a small plane to remove a section of wood along the length of the outer fixed cradle members. But it was actually found that most of the horizontal members weren't jammed up against the blind ends, and you can see that it's just the 4 upper members there that have begun to fill the space that we opened up at the side. As we began to remove the horizontal members, it became quite clear that many of them had been compromised with adhesive from the oak and beech blocks inserted between the cradle members. And here you can see a detail of one of the oak blocks bridging the gap between the fixed members, and also you can see the puddle of adhesive just here from the block above it that had fixed the sliding member. And you can see also how thick the block and the cradle are in comparison to the panel. This image shows the problem caused by the beech blocks that had been positioned cross-grain to the panel. The panel's been pulled backwards into a local convex deformation, resulting in fracturing the wood where the block meets the panel. And beyond that, you can see another fracture running off from the edge of an oak block. And the feathered edge that you can just see at the bottom is the edge of the facing paper. Finally, I just wanted to show this image, which clearly illustrates the incredible thinness of the panel. It's remarkable that it survived as well as it has, and it must be a tribute to the quality of the original materials and workmanship. The painting was kept within a temporary panel tray, which held the panel flat across the grain with horizontal braces while the structural work was being carried out. The sliding members and the wooden blocks were removed using a chisel, plane and laponite as before, and as the mahogany was quite soft, the fixed members could just be cut down with a saw and then removed in a similar fashion. Happily, the panel wasn't actually as reactive as we'd feared it might be, and it remained flat throughout the cradle removal. Partially this was due to the large number of fractures that were running throughout its length. And once the cradle was removed, the panel also came apart quite easily into the 3 pieces. You can see fairly clearly where the joins are there, just to the left of centre, and to the halfway down the right side there. The remaining join was not opened. It was very well adhered with good surface alignment, and we didn't want to cause any further damage to the paint at the edges of the boards. It's also worth noting at this point that there weren't any regions of rot or infestation or other damage to the timber, and although the panel was drastically thin, in places less than 1 millimetre, it was still in one piece. The facing was removed as and when necessary as each board was repaired. Clean fractures were repaired using clamps and props and supported under a bridge. And you can see here the wedges that were used when sideways pressure was needed. And many local deformations were also improved using moisture treatments and clamping. Old repairs were opened where necessary using laponite to swell the old glue, isolated from the rest of the panel with masking tape. The splits were repaired using a combination of adhesives. A fairly strong sturgeon's glue was first fed into the hairline fractures, and because of its low surface tension, this was drawn easily into the structure of the panel and wetted the surface for an application of EvoStick Resin W, which is a PVA adhesive. If there were any gaps, then a mixture of phenolic microballoons and coconut shell flour was added to the PVA, and this combination of filler and adhesive is going to be explored in the paper that Christina Young will be presenting later this afternoon. The adhesive was supplied from the front as well as the back, and the panel was gently flexed to help pull the glue into the damages. The panels were then set up with props beneath the bridge to realign the painted surface. And where there were gaps to be bridged across the splits, it wasn't always possible to reduce the dipping or batwinging of the panels on either side, but it was hoped that a new auxiliary support might help to improve these deformations. And in this image, you can just see a blade being used with a light behind it to check the surface level along the split, and you can see that batwinging that I'm talking about. And here are the 3 boards with all of the fractures repaired. Each one took on a more pronounced curvature after repair, as you'd expect. And there were also several regions that had lost part of the support and required inserts, in particular the join between the first and the second boards, as this join actually ran straight through Christ's body, leaving the diagonal lines in the composition out of alignment. It was decided to replace the missing millimetres to allow the restoration to be more successful. The inserts were made from oak, running in the same grain direction as the panel, and they were adhered with the same adhesive and filler mixture that I've previously mentioned. And so we had 3 exceedingly thin and highly fragile boards needing to be rejoined. But we weren't convinced that there was enough surface area between the boards to establish a successful and durable rejoin, even if the panel was to be given some form of additional reinforcement, such as a tray. Any sort of auxiliary supports using a series of localised points of attachment would be likely to cause new deformations. So some form of overall support, such as a balsa backing, was required. However, based on previous research carried out at the Hamilton Car by Al Brewer, we weren't happy using the traditional methods of balsa backing, using wax resin as an adhesive. The shrinkage of wax resin and the heat used in the application would risk putting such a thin panel under considerable strain, and it could cause pronounced warping or twisting. We looked into several possible adhesives. We were looking for something that would have bulk to cope with the irregular surface, had low shrinkage, a good bond strength, and wouldn't cause any undue movement of the panel either during application or on drying. An aqueous adhesive, therefore, seemed inadvisable because that would not only impart moisture and initially swell the wood of both the panel and the balsa, but the adhesive would also contract when the water evaporated. We tried to dissolve suitable PVA resins in solvents, but we found the working properties to be unsatisfactory, and we were unable to successfully combine them with fillers. So another material that we investigated was the carvable epoxy that George Bazarka was talking about earlier, that he recommended to us. And at the time, it wasn't actually available in the UK. So we tested 2 options: the PVA filler mixture that we'd used before in repair, and the 2-part carvable epoxy, Araldite AVNHV 1253. One was likely to cause undue swelling of the support, and one was epoxy, which is known as being hard and brittle and irreversible. However, this epoxy is designed specifically for use with wood. It's of a similar density, it's stable, it has a filler that allows it to remain carvable and therefore removable. It contains no solvents, and as it acts by way of a chemical reaction, it doesn't have any shrinkage. And so for these reasons, we chose a balsa backing adhered with a carvable epoxy. We also looked into an interleaf with the idea of reversibility in mind. However, we were very aware that we didn't want to compromise the bond that we would have between the balsa and the panel. A beaver-impregnated cloth was likely to creep and could also impregnate the surface with waxes. In fact, the Kozo paper that we'd used in facing the panel when adhered with sturgeon's glue proved to be an excellent barrier, but we obviously had the same issues about imparting moisture onto the back of the panel as we had previously. We were also concerned that perhaps we were confusing removability and reversibility. We didn't actually want something easily reversible because that would give a point of failure for the bond. The epoxy remains carvable, and so if necessary it can be removed mechanically. Before the backing was begun, the edges and the surrounding paint were faced with Kozo paper and sturgeon's glue. Should the adhesive actually push out and round to the front of the panel, we knew that it would provide a release layer. The balsa was prepared in 10-inch lengths. It was used in a standard width and at a consistent depth of 6.5 millimetres. In some cases, strips of balsa were glued together with resin W and cut to appropriate widths. A thin layer of epoxy was applied to the panel, filling the deformations and providing a bed for the balsa. And then a second thin layer was applied to the balsa blocks and combed off again to ensure that there was as little excess as possible. And in this image, you can also just see the oak insert here that I was talking about. The blocks were lined up along a metal bar and laid one by one in the same grain direction as the panel. The edges of the balsa, which butted up to each other, were also glued with the same adhesive. And each panel was then laid face down on an MDF support board, which was covered with felt, Melanex and tissue. And the balsa blocks were then clamped in position using MDF blocks to spread the load. And each of those MDF blocks had been chamfered to allow for a better working sight of the balsa blocks. And here you can just see the central board with the balsa clamped in place. Once the balsa backing had been applied to each board, the edges could be trimmed off and the 3 planks of the panel rejoined with a vastly increased gluing surface. And you can just make out the joins on the reverse there. Finally, we wanted to reduce any influence that the balsa might have on the panel in terms of movement in response to environmental fluctuations. Using a model maker's circular saw, we fashioned a jig from plywood and Dexian that would allow us to make regular diagonal cuts through the balsa at a depth of just less than that of the balsa. The saw blade was fixed and there was no danger that it could cut into the panel, but it was still quite a hair-raising procedure, but I'm not sure it's quite as hair-raising as what we just saw earlier with George's images. The saw was passed over the back of the panel in one direction at 3.5 centimetre intervals, and it was then reversed to produce a diamond-shaped pattern. And this is the reverse of the panel after the structural treatment. You can see that following the repairs and rejoining, it's taken up a fairly pronounced convex curvature, but this didn't seem to have increased from the individual board profiles that had been taken after the fracture repair. We observed the panel at different relative humidities, and it was quite clear that it still remained highly responsive to environmental changes. So that we could have some control over the panel movement, we prepared a framing device based on a hybrid of the previous auxiliary support used on the wings and the framing springs mounted on a central bar. The springs hold the tapering battens against the panel, exerting a certain amount of preload, which will hold the panel against the profiled slip frame that was prepared for the panel's curvature at 55% RH. The framed panel that you see here can be unframed by simply unscrewing the central bar from the build-up, and then the whole device comes away from the panel in one piece. And here is the front of the panel, restored and in its frame. And I've largely ignored the painted surface of the panel, so I'll just leave you with the restoration photographs of the triptych. During this presentation, we hope to have given a flavour for some of the practical techniques that are used in the restoration of panel paintings at the Hamilton Carr Institute and at Ebury Street Studios. We've also tried to explain our thought processes in developing a treatment for a particularly complex problem based on experience and on empiric judgment. Our treatment solution might differ from what other conservators would propose in the same situation, but we hope that the issues raised and the compromises sometimes required regarding materials, particularly in this forum, might spark some debate and help to inform future treatments. A panel 5mm in thickness is often referred to as a thin panel, and so a panel less than 1 millimetre in thickness is a whole different ballgame. Thank you for your attention.
Thank you very much, Britta. I should also say that since Britta's work and Ray's work on this panel, it's been on show in the Fitzwilliam, which has a slightly variable air conditioning system. And this panel has, you can see it has moved in response to the relative changes in relative humidity, but the whole structure has remained very stable for at least now, about 6 years. Well, it's now time for a break. We're very slightly behind time, but if you can come back very promptly from coffee, then after Marco Chatti's talk, we have time for a full discussion of the morning session. Thank you.